Yeah. So then we continue our lectures about different techniques that we use at synchrotron. And the next lecture will be about X-ray absorption spectroscopy, which will be done by Konstantin, beamline scientist and Balder Beamline. Okay, the stage is yours.
Yes. Okay, hello everyone. I'm Konstantin Klementiev, working at Balder at Max 4. I am in this business for quite a long time, measured my first exam some 34 years ago. So I can talk about this technique from my experience. Also, I have worked at a few synchrotron beamlines.
Big Balder.
All right. Yes, I will. You see the aerial view of Max 4. This is a 1-year-old photograph, roughly. You see two storage rings, one in this square building, 1.5 GeV, one in this larger building. Balder beamline is situated somewhere here on the larger storage ring. This is my intention, what I will be talking about. First, I will introduce synchrotron very briefly, and we'll talk briefly about emittance, because Max 4 is about small emittance. Also briefly about Balder beamline and absorption spectra that we produce at the beamline. And only after I will go to the general technique, the absorption spectroscopy, not inversely. Typically you see it inversely. Because I thought this is the way many our users see it. When young researchers come to us, they typically don't know about the technique, or at least we don't assume they know it. And so they first see the spectra, and then they start asking themselves, what do they mean, these spectra? So I will go roughly about this way. So show the synchrotron, and then the beamline, the spectra, and then go deeply. Yes, so if everything, well, if it holds the timing, then about 15 minutes will be left for questions. But if you have quick questions or your better understanding, just shout. If your question assumes a discussion, then better put it at the end. All right, Max 4, this is, well, you saw it at the aerial view. It consists of 3 accelerators. One is linear, or LINXS, that accelerates electrons and feed them to the smaller ring, halfway its length, and then full length to the larger ring. And also at the end of LINXS, there is a beamline. So LINXS itself is also serves as a photon source. What is special about Max 4 is that we have a small emittance. What is emittance? I will tell on the next slide. For a few years, we held world records. Now there are 3 more synchrotrons of this kind that will have a bit small emittance. Quite special also that we operate 2 storage rings, a small and a bigger. There is one facility in the world in Taiwan that do the same. Well, this is a bit more complicated, yeah, when you do it. Most typically, it is either, well, it's one ring, so it's either a lower energy or a higher energy. What is emittance? Emittance is a phase space volume, or a product of linear size times angular size. Or, well, so, and typically it is done separately in horizontal and vertical. So sometimes it is in one quantity, these 2 products, then it is product of 4 values. Why it is important to have small source size and small angular size? Well, first, small source size is important because our focal spot, the size of it is proportional to the source, you see, well, with some demagnification factor. Here I put some photographic lens as a, well, just general focusing optic. Of course, it doesn't work for X-rays. It's invisible light. Well, just for schematics. So the first reason is to have a smaller focal size. We have to have a smaller source size. In angular dimension, it is also frequently important because very frequently our optics can't take the full beam. We have to cut it, and so we lose flux. And therefore, not to cut it, we want to have it small in angular divergence. And then there is a third argument, which is increased coherence. This one is used by coherence techniques, some coherent imaging, coherent scattering, whatever. We spectroscopy, we don't care. So this is not about us. But the smallness of the beam, yes, this can be used. How is it achieved? Emittance, yes, as this product of two values, size times angular size, this primed value. Well, it happens to be proportional, to inversely proportional to n square, and the number of bending magnets. The storage ring, it consists of bending magnets that turn the electron beam. And so if we want small emittance, we want to increase this number of bending magnets. The older storage rings, they were so-called double bend achromat, where there were two bending magnets per what is called cell. So a periodic, a small structure that is periodically multiplied. In our design, we have 7 bending magnets, not 10. So then you can calculate what is 7 in power 3 compared to 2 in power 3. And so this is the factor, the gain factor that we have. And then when we pack together all these bending magnets, inevitably the size of everything becomes smaller and smaller, including also the pipe, the vacuum pipe where the electrons fly. And so that this pipe you see here, and also you will see it when you visit Max 4, there is a museum part. And so in all the synchrotrons, this pipe was really big. Now it becomes smaller, smaller, smaller. And this is a problem. You need to pump it, create very high vacuum, ultra high vacuum. And this was the technical trouble that stopped the development. And it was sold at Max 4 for the first time. And so that clever people proposed to make the pipe itself as a pump. So from inside, it was covered with a getter material, and it did work. This allowed then compactness and allowed the increased number of bending magnets. All right, we have on these 2 storage rings, and the smaller and the bigger, presently we have 16 beamlines, well, one also at the end of the LINXS. 16 beamlines, most of them are for spectroscopy. Most of them also for soft X-ray range of the photon of X-rays. And only one where I'm working, Balder, is for hard X-rays. I will be mostly talking about hard X-rays. Well, I will explain it later. Why? Because I am working there and because it has more parts in the absorption spectra. But this is also applicable, what I will be talking, applicable to soft X-ray range as well. Some beamlines, you see, they have some national flags. They are funded by these corresponding countries, but mostly this is funded by Sweden, and including these 12 Swedish universities. Balder is one of them, and briefly about the optics of Balder. Our source is Wiggler. This is a periodic magnetic structure. Electrons fly through this magnetic structure and make turns, and when a charged particle turns, it emits light. There are other types of similar periodic magnetic structures called undulators, and All other beamlines at MAX 4 are undulator based, and we are the only one which is Wiggler based. And the difference is that in the spectrum of the emitted light, Wiggler produces a very broadband spectrum. This is what we want because we want to scan very quickly at our beamline. And undulators produce a peak-like photon spectrum, which is also good. In the peak, the peak brilliance is higher. But then when you scan energy, you have to do something with the device. You have to scan the magnetic gap, which is never correct. A disadvantage of Wiggler that it produces a lot of heat. It generates about 20 kilowatt in the beam, and we receive only about 1 kilowatt. So then the rest we just waste to the cooling system. Okay, then we receive this beam to our optical hatch. I will show it on the photograph. Then with the collimated mirror, we make the beam parallel. We send it to the double crystal monochromator, these two crystals that select a single wavelength of out of this broad spectrum X-ray band. And then with toroidal mirror, we focalize it down to roughly 100 by 70 by 70, I say, the micron. What we get roughly 10 to 13 photons per second in the wide energy range. Well, at the end of this range, it is a bit less. So we start from presently from 4 kV, which is calcium KH and above, and there is no sharp upper edge. Maximum we've been at I think 55 kV. There is no much interest in going to very high energy. We focalize down to 70 by 70 micron, and we can defocus if needed. Vertically, we can defocus very quickly up to 2 millimeters. And we typically measure the speed of about 20 seconds per spectrum, but we can go down to a second or even half a second. This is a photograph in our optics hatch. The beam here comes from the right, then to the collimating mirror, mono, the focusing mirror, and out from this hatch to the experimental hatch. In the experimental hatch, we have this equipment. Here the beam comes from the left, while this big beast in the middle, this is our X-ray emission spectrometer. I will not be talking about it in this lecture. And the experimental table is on the right. On it, we have different equipment. Present on this picture shown this liquid helium cryostat, but we move it in and out. There is an arm that holds a 2D detector. We use it for diffraction if needed. And then on this side, there are two fluorescence detectors, well, shown only one, that we use to measure fluorescence, which this is one of the ways to record absorption spectra. I will come to this. In reality, it looks like this. On the left, this table, we have a big closed cycle liquid helium cryostat. The sample we mount here, well, sample plates. We have some adjustment system. This small device is an ionization chamber. I will also come to this. It measures intensity of X-rays after the sample in this case, and this is the arm that holds, well, it's now in park position, that holds a 2D detector for diffraction. The height, well, there is no scale here. The height of this table is 1.3 meters. This is what the users see when they come to us. The orange is I0, what we call, the green I1 after the sample. These two we divide by each other and take logarithm to get absorption coefficient. And this is what you see in the exhaust part. So on the right, well, now the second repeat started. And then on the right bottom, we see Fourier transform of it alive. And well, now the third repeat started. And you see that how this Fourier transform forms the atomic distribution peaks. First, they are very broad, but then as we proceed, they become sharper. and very well resolved. So these are 3 repeats, you see, fully overlapped, and this is what the users want. That's why they measure several repeats to tell the quality is good, noise is low, and repeatability is. So then, in principle, this is it. So after a few seconds, you move to a new sample or to a new condition of the sample. Frequently, we do something with the samples in situ, we heat up or do some chemistry, electrochemistry, whatever. In this case, this is a simple reference sample. This is copper oxide. We use it for analysis of other spectra of your interest. All right, so this is it from the experimental point of view. Now you ask yourself, what can I learn from it? And my lecture will be mostly about it. Yeah, well, but first about quality of other samples. This, what I showed on the previous slide was a powder sample. First here on the left, this is a spectrum of copper foil that I measured at different places at different times. So this in Hamburg, in Barcelona, and here, well, you see different years. And of course, as expected, we get the same spectra, basically overlap. The difference is in time. So in Hamburg, I measured the same quality in 15, 20 minutes. At Alba, some 2-3 minutes. Here we do it in a few seconds. And the difference is, of course, in flux. Well, flux here at Alba are comparable, but also in the quality of motion, of scanning motion. This is not trivial to get at very high quality where everything is synchronized. That's why we can do it very quickly here. All right, and then so also, yeah, here I also compare speed of copper spectra, 30 seconds, 1 second, half a second, and basically are the same. For foil, of course, you can afford going that quick. It's a strictly homogeneous sample. Not all samples are that perfect. Powder samples can be made homogeneous if you are skillful, or can be made horrible. And quality of spectra will depend on it. Liquids are homogeneous. Well, these are 2 repeats, quite good. And so this is powder sample, again, copper oxide. Also, so you see the repeatability in each figure. There are several curves. So the quality is well, super great at our beamline, provided the sample quality is good. Okay, now to the basics. What can we learn from it? And I will start with showing these graphs. These are interaction cross sections for 3 different elements: sulfur, copper, lead, depending on energy. You see there are 3 main interaction channels: photo effect, which is the highest, then Rayleigh, which is elastic scattering, and Compton, inelastic scattering. And the red curve is the sum of all 3. By green, I select the energy range of our beamline. And you see within the range of this beamline, photo effect is always the highest among the 3. Why I show this? To tell that the photo effect is the main interaction channel, so it's easy to measure. It's not something, you know, like magnetic scattering, which is super weak and you have to fight for it. No, this is very strong. So for all materials, or whether light or heavy, then should be easy to measure. Well, there are also collective effects. This is at the bottom of this slide, like Bragg peaks, where different atoms combine together, and in principle can be very strong also in scattering, in collective scattering, which is diffraction. Yes, that can overcome this the photo effect, but for a single atom, this is the strongest. What happens if we put our sample into the beam? I already assume it is monochromatic. So we measure intensity before the sample, we measure intensity after the sample, and then they are connected to each other with this Booger-Lambert attenuation law. From it, we can deduce this mu absorption coefficient, or rather mu d, but d is constant. And then we change energy, and so record this mu absorption coefficient as a function of energy. We will see something like this, what is called absorption edge, a sharp increase in photo absorption probability. What happens there, I will show, so at this energy, I will show on the next slide. But here first about terminology. The edge itself is, in our language, is called Zainis, X-ray absorption near edge structure, or, well, this is in hard X-ray world, or NEXAs, this is in the soft X-ray world. But this is exactly the same. And because the communities are separated by, well, geographically, first of all, hard X-ray communities, they reside on hard X-ray synchrotrons, and soft X-ray community to soft X-ray synchrotrons. And most typically, they don't talk to each other much, because soft X-ray techniques, they do typically a different kind of science, surface science, and whereas hard X-ray techniques, they do some bulk science. Yeah, well, so this is also a manifestation of separation of X-ray communities. Yeah, it does exist. And then also this wiggly part above the absorption edge is called EXAFS, and this is exclusively, it exists exclusively for hard X-rays. For soft X-rays, well, energies are not that long, energy scans, so it's not present there. Okay, what can we learn from this Zainis and EXAFS? I will tell later. First, about photoabsorption itself, close to the absorption edge. We have our sample, we illuminated with X-rays, and we want these X-rays to be absorbed by the material. We identify what's called central atom. Why I think that it is absorbed by this atom, not other atom? Well, because I select my energy close to the absorption edge of this atom. Yeah. And so then if I present the potential energy of this atom schematically, but it's blue lines, there will be some fixed levels, energy levels. The deepest is called 1s. There are 2 electrons there. And then there are next levels, 1, 2, 3, or 2s, 2p 1/2, 2p 3/2. Again, 2 electrons on each, and so on, m edges. And so that if we tune our energy close to this distance, and then if it is slightly below that that difference, nothing happens, because all levels are filled already with electrons. We can't then transit this electron to a already occupied state. But if we overcome the threshold, then yes, we can kick it out. And the difference, so the difference of the final state minus the Fermi level, it goes to the photoelectron. So we overcome the potential of this atom, and then it propagates as a wave, spherical wave, with that given energy. This wave is, well, it goes to infinity if it is a single atom, or it also bounces back by other atoms, including also returning to the original atom. So then there is an interference between these secondary waves, the primary wave. And here on this slide, I show constructive interference and destructive. And you will see similar pictures in every textbook. And the question is, where do I consider constructive or where destructive? I will answer it on the next slide. It's not obvious where we should consider the interference. It's between atoms. Here you see it is rather destructive, and you see here constructive, but no. This picture is destructive interference, and this is constructive. Why? I will explain in this. The theoretical description of this process of photoabsorption, it always starts with this so-called Fermi's golden rule. And This, well, it describes the photoabsorption cross section as a function of energy, as a sum of this squared matrix element, and the sum goes over the F final states. Here in this matrix element, this is an interaction operator that acts on the initial state I, and then between I and final state F, and the delta function stands for energy conservation. Those of you who took quantum mechanics courses realize this is not very quantum mechanical expression, because in quantum mechanics, when we add different processes, sub-processes, we add amplitudes, not probabilities. Here it is, you see this clearly, it adds, well, the square of the matrix element, it adds already probabilities, which seems wrong. But well, so there are, in textbooks, there are big chapters explaining why this is, why this works. For now, just believe it. So we postulate this is correct, and we will just continue with it. What is I? This is initial state that we select by selecting energy. If we want to excite the deepest electron, 1s, we know what is 1s. This is a spherically symmetric state. You see that radially is decaying quite strongly with minus ZR. If our Z is copper by 29, then the localization size is about 2 picometers. It's extremely localized at the nucleus. And well, this tells, this answers my previous question: where should we consider the interference pattern? Constructive, destructive, where is it? Well, everywhere else in space. It's this integral, the matrix element is 0, because this I is 0. It's only close to the nucleus where it matters. So that on the previous slide, where we consider constructive or destructive, it's only here in the center. We don't mind how these waves are interfere in other parts of the space. All right, F is unoccupied state. Well, actually, there are many unoccupied states, and this is the biggest problem in this expression. So to find them, there are methods to find them. But important is that these states are calculated in the presence of the core hole. They are changed by the presence of the core hole. And this is the biggest, say, question to the technique. We measure not the pristine state of the atom. We measure spectroscopically excited states. Whether they are similar to the original states, this is a big question. You need to answer it later. All right, and then in this expression, interaction operator is, well, it can have several forms. One is the product, scalar product momentum times vector potential. And then the vector potential is most typically expressed like this. So the polarization vector times plane wave. And then you say in dipole approximation, because R is very well localized, this is basically unity. The next term in this expansion of the plane wave, this quadruple approximation, is small. There is a fine structure constant, 1/37, and it's proportional to it, but also proportional to Z, the number of the element. For heavy atoms, like lead, gold, platinum, this Z is about 80. This actually is not that small, but anyway, everyone just neglects the quadruple transition when people calculate absorption probability. And then there is a equivalent representation or positional representation where it is, the interaction is just the scalar product, radius vector times polarization vector. Here at the bottom, I offer some math exercise. Well, I will not go into detail, just tell that it shows this math exercise that the interaction operator is proportional to first spherical harmonic, which tells it carries orbital momentum 1. And because of this, the final states and the initial state, they differ by orbital momentum 1. Otherwise, the integral is 0. And well, you've probably heard about this dipole selection rules from quantum mechanics that states that transition is possible with delta L. The L is the orbital quantum number, orbital momentum quantum number by ±1. I will summarize because this is the essence, the previous slide, the essence of the technique. So the base for your understanding what can be learned from the technique, I summarize it here. So photoelectric absorption is the main process. Should be easy to measure. Absorption spectroscopy is element specific because we can, by tuning energy, we can tune our initial state in that formula I. Due to selection rule, we can also be sensitive to some final states that we want. This is actually how we select the initial state. If we want to be sensitive to D states, if we study D metals, for example, this is the most studied objects, yeah, D elements. So if we want to be sensitive to D states, then we should start from P to have direct transition. And then, so absorption spectroscopy is sensitive to the feeling of the final bands. And when we'll consider the edge itself, then it means we are sensitive to valence of the elements. And also, you saw in that formula the scalar product R times the polarization vector, which means we have some anisotropy in respect to polarization of X-rays. We can use it. If our samples are anisotropic, we can rotate it around the polarization vector. Right, I move on. The EXAFS part, that was about Zanis or NEXAFS. The EXAFS part, I will not go into detail, just will give the final formula. First, we factor mu absorption coefficient into these two things, mu 0. This absorption coefficient a single atom would have without neighboring atoms. And then this part, 1 plus chi, and this is due to the neighboring atoms. We also go from energy dependence to wave number dependence by this simple formula. This is all quadratically dependent. K is the square root of energy. And then the final expression for chi, the EXAFS function, is this. So this is a sum over atomic shells. This and the sum is of well, sinus functions. The main term in sinus is the double. Well, the frequency of the sinus wave is the double distance, and then the amplitude of this sinus function is proportional to the coordination number and also some unknown yet function f, which is scattering amplitude, also inversely proportional to the square distance. And then inside the sinus, there is also a yet unknown function phase. The meaning of every theory is to calculate these two functions, the amplitude function and scattering phase. We don't know them yet. And so that either we calculate or find them somehow experimentally. And I will also show an example for this. If we consider the edge itself, there mu 0, this here is the main quantity there. Well, it's basically the edge itself, mu 0. And so we can't reliably calculate it. And therefore, the edge itself is mostly analyzed quantitatively. So it is interpreted. Whereas in the further part, in the EXAFS part, the main part is this chi, the oscillatory part, and we can analyze it already quantitatively. I will come to the examples right now. Okay, so let's get these formulas and look at our absorption spectrum. This is again a copper foil. So the blue is what we measure, and the red, this hypothetical mu0, we don't know. But we know this is a smooth function. So this is what an isolated copper atom would have. Copper gas does not exist. Well, in reasonable pressure. So we can't really experimentally measure this. Well, single atoms of copper in absorption spectroscopy. No, we can only measure foil or whatever. Well, maybe liquid if we go very high in temperature, but not single atoms. So this mu0 we can't measure experimentally. What we do, we just smooth out these blue wiggles and tell when it is smooth enough, this is probably our mu0. So we subtract it, divide by it, and get this chi function experimentally. And we know well, this is it. I also here multiplied, well, I changed dependence from energy to photoelectron wave number, and then also additionally multiplied this function by k square to, well, this is a growing function, k square, to compensate the decrease in the amplitude here. And we know this is described by this formula. So because these are modulated sinus functions, the natural way to analyze it is to take Fourier transform, of course. And we expect for every sinus function a peak. And this is indeed what we see. So after Fourier transformation, we have a series of peaks. Each of them correspond to the, well, to a member in this sum. These are what we call coordination shells. Atoms form some similarly distant groups from the central atom. In copper, there are just 12 numbers, 12 neighbors. So the coordination number is 12. The next is, well, in the next shell, there are 4 and so on. So then this first peak corresponds to the first coordination shell and so on. So then, well, we are happy, kind of. Yeah, we measure the spectrum, we see at its Fourier transform, and this we think of as a atomic distribution function, but it is not. So if we look at the peak positions here, we see that the first peak is at 2.3 angstroms, whereas in copper, we know it's what we can find out it very quickly by diffraction. The real distance is 2.55, quite a big difference. So then, first, why does it happen? Well, it happens because of this phi function. So this scattering phase. You see, it's, well, the linear part of it is, well, it modifies the distance r. And what is also quite trivial is that this function is always negative. So the shift is always towards smaller distance. What is, well, and this is quite an unpleasant story about EGDOS. It doesn't give the real atomic distribution. It is always shifted. But what is yet more unpleasant is that this shift is individual by peaks. Every peak is shifted individually. So then what we do? Well, one way is to find a good theory and calculate this phi function, well, also f, the amplitude. And another way is to use similar structures. Both, they work. And so the calculation is most typically done by this program called FIF. It was developed in University of Washington in Seattle, and more or less every EGZAFS researcher uses it. Another way is to use experimental spectra of known composition, known structure, which is very similar to your unknown. material. For example, if I measure two foils, copper and nickel, and just overlap them. Of course, absorption spectrum of nickel, well, these are neighboring elements. Both have FCC structure, so face-centered cubic. And well, absorption edge is, of course, they don't overlap. At about 9 kV, this is copper, and about 8.3 is nickel, but I just shifted it to match, to see how they overlap. The edges, well, the edge is very, well, similar, but I want to analyze exers. And we see, well, it's also very similar, just the frequency is different. Our frequency is, remember from the formula, is double distance. So yeah, distance in nickel is slightly less, shorter, so that frequency, what we see is slightly less. And also, if I take Fourier transform, I see that, well, this is the same structure, FCC structure, just shifted a bit. So I can extract amplitudes and phases from this Fourier analysis. This is very simple. And using it, I can, from copper to analyze nickel, or from nickel to analyze copper. So here I did to analyze nickel from copper, and then I get by fitting, I get 2.47. Is it good? Well, if you compare to the real distances, the real is 2.49. Nah. So 200 angstrom, which is off, whereas fitting error is in the third digit, but so the actual difference is in the second digit. And the coordination number we note is 12 for FCC, but it's 12.6 with the fitting error 0.3, which is also off the range. So if you are not very picky to the results, yeah, you can use it. But most typically, yes, people use calculations, and they work quite well. When is the finish? Okay, yes. Then we'll come to considering what can be learned from Zainis on nexers in soft X-ray vocabulary. So this picture I've already shown. This is a schematic potential and potential levels of electrons in an atom. And then what can happen if we tune our energy close to the edge? This is where we have Zainis spectrum. Yeah. So first we can have resonances. Close to Fermi level, there can be localized but free states, or free but localized. Typically, when it's free, it's continued. It's not localized. When it is far from Fermi level, but close to the Fermi level, is still localized. So when it is free, in principle, we can transit our deep electron, 1s electron, to this free state, and we will see it as resonance. So because probability, if we tune our energy to this energy difference, then the probability is quite high. You will see it as a peak on absorption spectrum. What is also different in the real world and spectroscopically excited world, that the levels close to Fermi level, they are actually shifted down by the presence of the core hole. And so that when you look at these resonances as a pre-H peak or as the mainline peak, then you should understand that the Fermi level is somewhere above. So somewhere here. Also, typically people think absorption edge is most typically people define as the maximum of first derivative. But this is not the case. So actually Fermi level is somewhere on the right, because these free states, they're shifted down in energy by the presence of the core hole. Then there are effects called shake up or shake off. In addition to our primary transition, there can be some smaller in intensity secondary transitions. So we share energy between this transition and also another transition from a shallower level to another free state. We can see them sometimes as some secondary small absorption edges. Also, there is an effect called shakedown, where the core hole is filled not by electrons from this same atom, but from the neighboring atoms. All these effects, they complicate the picture. So you should know about them when you make some conclusions from your spectra. Anyway, the main visual results from your spectra are these pre-H peaks and the white line peaks. And I will now give a few examples to explain how this can be used. So first example is the pre-H peaks. And again, I remind this selection rule, dipole selection rule, the quantum, the orbital momentum quantum number can be changed by 1, plus minus 1. And so if we consider now K absorption, so that the initial level is 1s, the final states, according to this rule, should be P states, right? But now if we consider D elements, whatever, 3D, 4D, 5D, we know that the states close to the Fermi levels are D states, because these are D elements. So directly from 1s to D, close to the Fermi level, we can't go. And but this is true only for this transition selection rule, is only true for central symmetric case. If by whatever means you break the central symmetricity, then it doesn't hold anymore. Or there is another wording of it. You do PD hybridization, or another wording, your final state have some P projection. These are all the same equivalent wordings. But the effect is that when the central symmetricity is broken, then the transition from initial 1s to this final state close to the Fermi level is possible. All right, and let's look at the absorption spectra. Here, well, I took it from this paper, and these are all molybdenum oxides, and these are all distorted oxides, so distorted structures, except the molybdenum dioxide, which has 6 oxygens around the molybdenum atom. Well, this is stretched octahedron. Still, it is central symmetric. So the equatorial are closer, the apical are a bit longer, but this is central symmetric. And indeed, when we look at the absorption spectrum, because it is central symmetric, the direct transition to this some free states below the Fermi level are forbidden. You see? And well, they are possible for these distorted states. This is a very simple experimental evidence or experimental information about your sample. So by the presence or absence of the pre-H, you can tell what is the symmetry of your coordination of, in this case, molybdenum. So without any calculations, yeah, very qualitative, but already something. Another example is from this paper by François Farge. They looked at various titanium materials, reference materials, they know the structure of them, and they put these materials into this two-dimensional plot. In abscissa of this plot is the position of the pre-H peak, well, similar to this one, but well, it's a bit sharper for titanium. And in ordinate is the height of this pre-H peak. And so that you see they are grouped. It appears that they are grouped by, well, into these 3 groups. And within the group, they know this is 4 coordinated titanium, 5 coordinated titanium, 6 coordinated titanium. So then you measure your sample, you define the peak position and height, you put it on this plot, and you already tell how your titanium is coordinated in your sample. Also, very simple, with just very trivial analysis, you already have an answer about your material. Great. Move on. Yeah, also the edge position here, you see it for molybdenum, I can show it. It depends on the formal valence. Molybdenum dioxide is the valence is 4, and all the rest is higher, up to 6. And so you see the edge position is shifted depending on the valence. And so molybdenum foil would be somewhere here at 20,000. So if we put the edge position as a function of formal valence, like on this plot, it's also from the same paper, you see a linear plot. So in the same way, you define from your experimental spectrum, you define your edge position. It's also a question how to define it. Well, most typically by first derivative, by the first maximum on the first derivative. So you put it on this plot and you tell what is the other the valence of your sample. Also great. And then a similar example about chromium. So it also forms a linear, but basically every element forms this linear dependence, just you need to know it. Well, you need to find in literature, somebody has measured it already probably, or you measure your references yourself, define this plot, and then put on this plot, you put your point for your unknown material. Okay, I will skip this. Yes, coming to the white line, the main resonance. What is it? Historically, this sharp peak on the absorption spectrum is called white line. And the height of it is proportional to the number of free states in your atom. Here on this plot, well, I took it from that paper, they shifted all 3 absorption edges from 5D elements, from gold up to, from rhenium down to gold. Up to gold. Gold is the highest number there. And you see for gold, there is no D state free, all taken, and there is no white line. For platinum is 1, and so on. And so that it is, well, the white line integrated intensity is proportional to the number of free states, which is also, it tells you about valence. If you change it, you can oxidize them and see how it changes. Yeah, this is also very informative and very frequently used by our users when they, especially in situ, change oxidation state of elements. There are some difficulties in this way. In particular, in that paper, they show that the white line intensity also depends on the particle morphology, which is not directly the oxidation state or the number of free states. So it complicates it. But if you compare with reference materials, then yeah, it generally works and is used by our users, by users of the technique. Before I go to EXAFS examples, I show this effect of temperature. We can change temperature of materials by putting it into a cryostat and measure it in just at some low temperature. Most popular is liquid nitrogen temperature, what's called LNT here. And you see the effect. So if here I compare copper foil spectrum at 2 different temperatures, room temperature and liquid nitrogen temperature. The edge itself here, you see it's basically doesn't change. But EXAFS, yeah, it does change. You see the blue, the amplitude is, well, significantly stronger. Also, you can see it on the Fourier space. So this is a good justification that, yeah, you want to measure at low temperature. It's just spectroscopically more information rich. It's technically, of course, a complication, but still many people do it because it's better. If you can do it, do it. And then another example, this is silver silver foil at yet lower well, this is a series of temperatures. Well, anyway, the effect is the same. So this is an explanation why we want liquid nitrogen here. So I come to an experimental setup and then an example of catalysis research, if I have time. I want to stop at 12.5, I guess. That's 12.05, yeah? Oh.
12:20.
Sorry?
12:20.
Okay, but this is 15 minutes for questions. I want that. All right. So experimental setup is schematically shown here. We have our X-rays from our synchrotrons through the optics and monochromator, and then it comes to us. And we measure intensity in front of the sample by this I0 device. It goes through our in situ cell. I schematically showed it here. So that has heating and cooling for the reason I showed before. And we put our sample somewhere inside. Also, frequently, we put it in a gas environment. We want to change it for catalysis. And then we measure intensity after the sample. In reality, it can look like this. So this is about 10 centimeters, the length of this cell. The beam comes from here. There is some argon line to blow the window here so that it doesn't freeze. Some heating wires, cooling wires, and we put materials inside by unscrewing the screws. Another implementation of an in situ sample with liquid nitrogen tank above it. This is self-flowing liquid nitrogen, and then sample sits here. Well, the length is also about 10 centimeters here. All right, and an example, I will try to make it quick, of catalysis research. And in this example, my collaborators, they prepared two catalysts, palladium on carbon black and platinum on carbon black. Well, they were characterized by different techniques and so on, and the result is about 1 weight% in each case of platinum and palladium. Then what we did with the sample, well, both samples in and in situ cell, what I showed, we do stepwise reduction. So we elevate temperature with some, well, step 50 degrees, shown here, and we give a hydrogen stream. At that time, we couldn't have pure hydrogen. Now at our beamline, it is possible. At that time, we can only use 5% diluted hydrogen. And so you do this stepwise reduction. When it is, well, the steady state is reached, then you remove hydrogen, put helium, and cool it down to liquid nitrogen, measure spectra, and so on, step by step. These are the resulted spectra. The top part is for palladium, the bottom part is for platinum. The left column is in EXAFS space, and the right part is the Fourier transformed space of this left spectra. What we see there are some references. So palladium and platinum foils, the blue ones, and also oxides, the green spectra. These are just references. From the references, you see what is the first coordination shell. No, that's not the green. In this case, this is purple palladium oxide. So the first shell is the oxygen shell. And then as prepared sample, the green one is very similar to the oxidic state, and then nothing at higher distances. And when after the first reduction step, what we have similar structure, similar to the metal foil, just smaller intensity. So we already formed some metallic particles. You see it right from the spectrum, but they are small. And when stepwise we increase temperature, these particles grow in size, grow without saturation. And for platinum, this is a bit different. We start from initial state, green, which is very similar to the acidic in the first coordination shell, but also smaller. And then after the first reduction, it forms some particles that are very similar to the metallic, again, much smaller in size, and it stays. Whatever you do with further temperatures, it doesn't grow. So these are two similar but different cases. All right, I think I skipped this. So how you quantitatively analyze and to fit it and to extract distances, coordination numbers. I think I don't have time. I will go right to the end of this story. And so that from the spectra, we can extract coordination numbers. And from the coordination numbers, we can calculate cluster radius, assuming these are spherical particles. Of course, this is a very strong assumption. Maybe they're not. But while assuming it, then we can see it also in size. You see this sub-nanometer particles. And in palladium case, they are growing, the particles, whereas for platinum, they are just fixed in one point. And that point corresponds to a 13-atom cluster. Just first atom and 12 around it, and nothing more. This is not the story. When you publish a paper, you always tell a story. And the story was that these catalysts, they were used in real catalyst process. I don't remember it for what, but they saw poisoning of the catalyst. So after some time of work and also, well, temperature history, they stopped working. And the question of what happens to the catalyst? Well, by this temperature programmed reduction, we don't see that they sinter. The very first suspicion in catalysis is that the particles, they just lump together and the surface area, well, the specific surface becomes smaller. So, well, you block your surface. But this is not what we see. And so the story from that particle, from that paper was that, yeah, we don't see sintering. And this is already important for catalysis, for this particular catalyst. So it's rather what we then hypothesized, the support itself, carbon black, covers the particles, which was also supported by other methods. All right, this was an example of how to use RIXS for a real study. I will briefly go through detection. This is important for our technique. There are three main registration techniques in transmission of fluorescence and electron detection, and I explain it here briefly. So if we excite an electron from a deep level, from 1s to continuum, or from another level, P to continuum, then a hole is left, and this hole is then refilled by other electrons. And while refilling the hole, well, of course, according to the transition rules, while refilling it, then two things can happen. Either these upper electrons, they emit radiation, fluorescence, that we can record, or there's also Auger process that, well, this is simultaneous relaxation and excitation of another electron. And then we can record these electrons as current. So we can use this picture for our purpose. We can record fluorescence or electrons also as a manifestation of the main absorption process. All right, I will keep this discussion. In fluorescence, also there are differently intensive lines, K alpha lines, K beta, and the intensity depends on the occupants of these levels. I will skip it. There are three basic ways for us how to measure intensity. One is in transmission, just through the sample. This is what I showed right from the start. And we measure intensity in front and behind the sample with ionization chambers. One second way is to measure fluorescence by some semiconductor detectors. We have both germanium and silicon detectors. We use them for different energy ranges. And we can measure total electron yield, well, by simple current. So we just apply some bias to a neighboring electrode and measure current from it. The ionization chamber is a simple device. This is basically a flat capacitor that you put in a box. In that box, you put some gas at a given pressure. You select that gas depending on the energy of X-rays. And what happens when X-rays ionize the gas? You know that X-rays are ionizing radiation. Yeah, so it ionizes gas. It then kicks electrons from atoms. And then if we apply high voltage here between these two plates, then ions, well, this negatively, ions fly there, electrons fly to the other direction. And from that collector electrode, we can connect electrometer and just measure the current. And this current will be proportional to the intensity of the incoming beam. There are some complications there. We should properly ground it. Otherwise, well, we can destroy, this is a relatively weak signal. But the basic principle is very simple. Fluorescence detectors, well, these are just examples. We use more complex devices. This is single pixel and quite small pixel device, but it's very cheap. And so what it produces is a spectrum like this. Here, scatter means elastically scattered light. So in this case, you see the excitation was around 8.6 kV. And as we scan energy, when we measure absorption spectrum, this would go to the right, to the right, to the right. But these characteristic lines, you see iron K alpha and iron K beta, they stay there. And what we do, we then digitally integrate these signals within a given window. And this integrated signal is proportional to, again, to the absorption probability. And the third way is technically very simple. The size of this, well, this is lying on the table. The size about 10 centimeters, this is about 1 centimeter. So you see a copper foil, and we put X-rays somewhere here, and just a millimeter away, we put a small nozzle, metallic nozzle. We bias it 100 volt, and then electrons that are emitted from this photo, they are collected by that guy, and we measure current there, which is again proportional to the absorption process, absorption cross-section. So these are three ways, and how to select them, well, it depends on your sample. And yeah, I think I skipped this. It depends on your sample. For bulk samples, simple samples, foils, pressed pellets, we always use transmission. But sometimes your samples are very diluted, some millimolar or sub weight percent. And then you have to do something. So in transmission, you become the edge jump. So the absorption contrast become very weak, and so that noise level becomes high, and therefore you go for the alternatives for fluorescence or total electron yield. Fluorescence is mostly used. Total electron yield is very surface sensitive, whether you want it or not. So if you want it, yes, you use it. For soft X-rays, this is, I think, much more used than for hard X-rays for two reasons. One is that quantum yield of fluorescence, it's energy dependent or Z dependent. And so at lighter elements, Auger process is more probable than fluorescence. So just this signal is stronger. And also the second reason is that all soft X-ray beamlines, they're basically surface science beamlines. So you want to be surface sensitive, and therefore you select this registration, total electron yield. And for hard X-rays, basically we are most frequently interested in bulk structure, and so that we use fluorescence. Also, the quantum yield there is high. Okay, samples. Yes, very shortly, I will go through this, and I think this will be it. You can find good tutorials on how to prepare samples. I can recommend these two, but you can Google for other maybe good lectures. And so with pictures, they show what to do. The general requirement when you prepare samples from powders, most frequently your samples are powders. The samples must be homogeneous. So not very big bulk particles that act as beam stops, and also not with pinholes between the particles. So both cases, very large particles and pinholes, they destroy the quality of the samples. So then the solution is to grind your powders to a very fine powder, ideally to the particle size smaller than the absorption length at this given energy, which in practical terms is below 10 microns. By eye, you can't tell it. It's most practically, it's just by time of grinding. Okay, and then so that aggregative states that we can use, we measured most typically solids, but also frequently we have projects with liquid samples. Liquids are very simple. So with this simple container consisting just of two carton sheets, with a say a millimeter space, you inject your liquid, and this is it. So most frequently it works nicely. And the concentrations that we can reach most typically with our sample or with samples from our users, this is in transmission more than say 1% or not much less than that. And in fluorescence, yeah, we typically it's set here, but we measured in 1 ppm as well. Okay, I think I skipped this. This is a way to calculate your powder samples before you make your pellets. There is a program where you give your chemical composition, you give energy and optical thickness of your pellet, and it gives the mass that you must weigh and then grind, press. We use these press forms, most typically 13 millimeter dies, but also 5 millimeter if you have not much of materials. 13 millimeter is easier to handle. That's why it's more popular. And then we press it using this press. I think I skipped this. Yes, and just a few minutes about radiation damage. This is an important topic, especially for us. We are a very powerful beamline. There's a lot of flux in the beam. And so sometimes we destroy the sample. And especially sensitive are samples containing water. This is the worst case. Water is split by X-rays with what's called radiolysis. And what is then formed is hydrogen as bubbles, you see, especially from liquids, and hydroxyls. Hydroxyl is extremely aggressive. It changes chemical state of your sample. And so this is what is radiation damage. And I put a few pictures here from these two papers. So they measured copper foil just as a reference, but then they start from their sample from just initial state and just by time. So they don't change their sample in situ by heating it or by giving some reducing agent or whatever. You see, then it goes from here to closer to the metallic state. Oh, and what is the metallic state? You see it by the copper fall. So it reduces, well, by this hydro field. This radiation damage is, I think, almost exclusively seen as photoreduction. From initially oxidized state, you see it, it goes to some reduced state. And here's another example. Is also from initial oxidic state, then it approaches the metallic spectrum. Yes, if it happens, then you need to invent something. So this most obvious is to measure quickly, and that's why we invested a lot of effort to scan quickly. So that I showed you example of half a second. We can continuously do 2 Hertz acquisition. So that this is in full excerpts, 2 Hertz in hours. Yes, and so that in the first spectra you see the pristine state, and then you see in time it develops, and then of course you tell that yes, I throw away all this and I use the initial state. Another way of dealing with it is to cool the sample. That's why we have helium cryostat. It helps a lot. So it slows down reduction. Yeah, this is another example. This from peptides, Alzheimer's disease related, containing copper. And also you see in time, it starts from here and then it goes to more reduced state. But initial first few spectra we could use, which is, this is a demonstration that copper is sensitive, but iron with the same material, but that has iron is not. So yeah, you first demonstrate it works or it doesn't, and then you do something. Measure quick, or sometimes you feel lucky, it just is not sensitive. All right, I think I conclude here. And I showed you briefly the beamlines of Max IV, including Balder. And I talked about absorption spectroscopy, showed a few examples in Zanes and EXAs. Both are suitable for reaction conditions because at hard X-rays we don't need vacuum. I didn't tell it, but I guess you know it already, that EXA doesn't need long range order, and this is in contrast to diffraction techniques. So any material can be used. It's absorption spectroscopy, not only crystals. Okay, and so from Zanes, I showed a few examples where symmetry information we could extract and valence state. And EXAs, I showed a few examples where interatomic distances and coordination numbers we could extract. All right, I think this is it. Thank you.